The unexplained blue shift in the radio signal from the Pioneer spacecraft is well established. The Pioneer anomaly is experimentally observed as the residue of a frequency shift after the Doppler shift effect is subtracted by expressed as an apparent acceleration. This is based on a notion that the Doppler shift applies to the residue. This assumption is unsupported. Another unsupported assumption is that the blue shift is sun-directed. The Pioneer anomaly could be an effect other than a real acceleration, such as a time acceleration or an effect of an unmodeled effect on the radio signals. Although unlikely, a currently unknown systematics effect is not entirely ruled out. An obstacle to a new gravitational physics explanation of the Pioneer anomaly is that a modification of gravity large enough to explain the Pioneer anomaly is in contradiction to the planetary ephemeris, unless the equivalence principle is violated. The accepted opinion is that cosmic dynamics, according to general relativity, has far too little influence in galaxies to be measurable, and that the expansion of the universe is essentially negligible for scales up to galactic clusters. Further, the expansion of the universe indicated by redshift has a sign opposite to the acceleration. Data for the existence of the acceleration from Galileo, Ulysses, Voyager, and Cassini spacecraft are suggestive, but inconclusive. The currently accepted explanation is that thermal radiation from the spacecraft exerts a sunward recoil force. The problem: there are several other characteristics of the data that are ignored. The scalar theory of everything model for the Pioneer anomaly is that matter causes a static warp in the plenum that causes the effect on the signal. The gravitational attraction, the equivalence principle, and the planetary ephemeris remain as described in general relativity. Therefore, the equation used to calculate the redshift for galaxies applies, where the matter acts like sinks in the equation and the observed blue shift is the negative of the galaxy redshift. You can see my video about redshift. The amount of warp, rho, at a point in space was posited to be equal to the gravitational constant times the mass of a body divided by the distance to the point. And to get rho at a given point, you sum over all masses. The equation for the calculated redshift is as in the galaxy redshift. The terms are defined in the redshift video except for DL is twice the distance, and two of the terms are zero because the distance we're concerned about here is small relative to galaxy distances. This is the data for Pioneer 10. The diamonds are the data, which are here, here, and here. The squares are calculated, and you can see it's a pretty good fit. The X's here are calculated for dates 10 days from the date of the data, and that's because the duration of taking a data point has been about 10 days. This is for the Pioneer 11 spacecraft. This point here is the Saturn encounter, and you'll note that before the Saturn encounter there looked like there could have been a redshift here, but a very slight blue shift at least. Then the Saturn encounter had a very large error associated with it, and these are two things that are unexplained by the current model. Because the value of the acceleration depends on the closeness of matter to the line of sight, a change over 10 days or longer is due to long integration times. The correlation coefficient we saw in these two previous graphs is about 0.93. The following are the other observations of the Pioneer anomaly that are poorly explained by other models. First is the annual periodicity. Anderson noted an annual sinusoidal variation in residue of the data. Sinusoidal means a circular motion around some point at a constant radius. Such a motion is the apparent motion of the Sun around the Earth. There's a sine term, is the distance of the Sun to the line of sight. Line of sight to the spacecraft. The angle we're concerned about is Sun, Earth, spacecraft, and this is then the sine of that angle. If the angle Sun is large, in this case where the Sun is on the other side of the Earth from the spacecraft, then we get a nice smooth 1/r kind of distribution. If the angle to the Sun is small, then we have the effect of the Sun on the electromagnetic signal. You will note this is similar to the discrete redshift. The same applies to the sidereal periodic motion. That is to say, the send and receive station of the signal is on the surface of the Earth, and there's a constant radius between the center of the Earth and the radio station. The difference in the acceleration between spacecraft is because the outer planets are on the opposite side of the Sun for P10. The effect of the planets on the acceleration of P10 is less than on P11. However, as d of the P11 increases, the planet's effect approaches a constant value. The stoe expects the galaxy mass to have a small difference between the spacecraft caused by their different travel directions. The orbit of P10 is closer to the Sun's Sagittarius A axis than P11, and the distance of P10 is greater than the distance of P11 because it's been in space longer. Now, the Sagittarius A is where we think the source in our galaxy is located. However, the effect here is within uncertainty levels. The difference between the two programs' methods for analyzing data are different in the early stages of the Pioneer 10 and closer in agreement at the later stages of the Pioneer 10. The varying acceleration may explain the difference. The AP is not constant, as one of the programs assumed. The slow decline in the acceleration, the radio signal measurements are from the and to the Earth. At small distance, the relative effect of the Sun-Earth distance is larger than at farther distance. As d increases, the solar system effect appears to approach a single mass located at the very center of the solar system. Therefore, the acceleration declines and approaches a constant value dictated by the rho being inversely proportional to the negative of the distance. However, the stoe expects that at much greater distance, the effect of the galaxy mass will increase to cause a difference in the AP values between the spacecraft. This plot shows the acceleration varies widely over a period of hours closest approach of P11 to Saturn. The negative acceleration calculation is a redshift, as seen in the previous figure. Data at the beginning of the encounter has a near zero blue shift. A large uncertainty in the second P11 data point is the Saturn encounter. This data point extends over a relatively long time, some 50 days. The rapidly varying acceleration in the previous slide is consistent with the uncertainty. You'll notice the angle of the Sun is nearly on the other side of the Earth from the spacecraft, and so it doesn't play much of a role. The cosmological connection. Here's a plot that we had in the redshift video, where we have distance versus the x factor, and we see something very similar to what we saw in the redshift video, except that the sign is different. There's the formula for the graph like we did before. This has a 95% correlation coefficient, and we calculate H0 to be 106. The Pioneer anomaly and the redshift of cosmology are the result of the same rho effect on light. In the cosmological redshift calculation, the z follows the Hubble law if rho is inversely proportional to the radius. In the gravity well, the redshift follows a negative Hubble law. That is to say, rho is inversely proportional to the negative of the radius. hence the negative of the galaxy redshift cosmological constant. Galaxy redshift and discrete redshift are the same phenomena as the Pioneer anomaly. Predictions of the stoe in 2006 concerning the Pioneer anomaly that no other model predicted have been published later in 2009 and 2011, and these are the two papers it was published in. Because the Pioneer 11 data before the Saturn encounter was near zero, the accepted explanation was there was no Pioneer anomaly before Saturn. The data before the flyby encounters were insufficient to detect the Pioneer anomaly. That's what the paper showed. The stoe requires that to be the case rather than that there was no Pioneer anomaly before the Saturn encounter. The Earth direction is marginally preferred. Other models, including the thermal recoil model, consider the Pioneer anomaly to be sun-directed. Earth-directed implies a signal effect, which is what the stoe has. We quote, "The data favor a temporarily decaying anomalous acceleration. The decline is exponential according to the stoe, except when the signal passes near a large mass, such as during flyby maneuvers." The stoe model, all the data of the Pioneer anomaly is not just the one type of data. The stoe model has made predictions that have been discovered later. The stoe model is more universal because the physics is the same as for galaxy redshift.